And it is my pleasure to introduce you Wesley Holliday, who is professor at University of California, Berkeley. He has published on quite various range of topics, all of very strong interest for our group, for our Milano logic group. In particular, he has published on voting mechanism, on semantics for modal logic, alternative semantics for modal logic, possibility semantics, in general in algebraic methods in logic. But in particular, he has published on a lot of interesting research on the connection between logics and probability, and this will be the topic of today's talk, that is logics of imprecise, comparative, and regular probability. So I will leave the to
Thank
Professor.
you very much. Thanks, Paolo, for that kind introduction. It's an honor to be here. So thank you, Paolo, for the invitation and the other organizers. When I was looking at the website for the Milano Logic Group, I was really impressed by the description of your interests, and that led me to choose the topic of the talk today. So logics of imprecise, comparative, and regular probability, that's kind of a mouthful, but I will explain how these different pieces fit together. And this is joint work with Yifeng Ding, who's actually graduating from Berkeley this semester and moving on to Peking University, and then Thomas Eichardt from Stanford. So this is based on a paper forthcoming called Logics of Imprecise Comparative Probability, as well as work in progress. So I gave a similar talk to the Moscow Logic Group recently, but without the work in progress. So the part about regular probability, that is new, and that's what I'm going to be trying out with you today. So the basic plan is to review, and I think for many of you, given the interest of the Milano Logic Group, this will be review, to review comparative probability and imprecise probability. Then I want to also review some famous and less famous and new representation theorems. Then I'll turn to logic proper. So I'll introduce a formal language, and I'll talk about formalizing reasoning about comparative probability, whose semantics is given in terms of imprecise probability. So I'll also add various bells and whistles on top of the basic reasoning system. So I'll talk about adding epistemic modalities. I'll talk about dynamic epistemic logics for updating imprecise probabilities, and dynamic epistemic logic for becoming aware of a proposition. And finally, and this is the new bit, I'll talk about a debate in philosophy about regularity for probability and how that interacts with imprecise probability. Okay, so that's the plan for today. And stop me at any time if you have clarification questions. So comparative probability. So the idea is one school of thought in the foundations of probability thinks that you should take as your primitive concept, your starting point, the notion of at least as likely as or more likely than, where this is a binary relation between propositions or events. So this is the symbol that I will use to mean that A is at least as likely as B. And the idea is we can ask what axioms should such a comparative likelihood relation obey? And here we could be thinking of it as a kind of subjective probabilistic judgment. So we could ask, what would a rational agent, what axioms should a rational agent's relation obey? Or we could have something more objective. As an example of an axiom, which you might think, somebody's rational judgments of at least as likely as ought to obey, we have the so-called qualitative additivity principle, which says that if you have some proposition C, which is disjoint from both A and B, then you should judge that A is at least as likely as B if and only if you judge that A or C is at least as likely as B or C. Now, of course, if you make your comparative likelihood judgments on the basis of a finitely additive probability function, then it's easy to see that this axiom will be satisfied. But we're not assuming that you have a numerical probability that determines, taking as our starting point, the qualitative judgments themselves. Now, you could try to give various arguments for why it's rational to obey this principle, some kind of pragmatic decision theoretic arguments. but I won't do that today. I'll just leave you with this to contemplate, consult your intuition whether you think that that's a reasonable principle for at least as likely as. Now, the mathematical question is, when is such a binary relation representable, and I'll define what that means, by numerical measures of certain kinds, for instance, Kolmogorov's probability measures. Okay, so this is, of course, a big topic in measurement theory. And when can you represent it with an appropriate numerical structure? Piece of my story is imprecise probability. So this is another school of thought, and this critiques the assumption of standard. Every proposition is assigned a precise probability value. So the idea is that we can represent a state of uncertainty, the subjective probability perspective. We can represent a state of uncertainty not just with a single probability measure, but with a set of probability measures. So if I want to describe the uncertainty of an agent, I might attribute to that agent a set of probability measures. Our probability measures. Okay, so we say A is at least as likely as B, just in case every measure in our set P says that the measure of A is at least as great as the measure of B. Okay, so that's a unanimity relation. And in that case, I'm going to say that this binary relation is representable as the weak relation. It's the at least as likely as. Okay, so that's why it's the weak relation. And shortly, I will also talk about representability as a strict relation. So again, we can ask now a representation question, but now the question is, what axioms on a binary relation are necessary and sufficient for the existence of a set of measures? And you might then want some conditions on the measures, some convexity or something, but in the first instance, just the existence of any set of measures that represents your given binary relation as the weak relation. Okay, so that's the question. Now, before I give the answer to what are the necessary and sufficient conditions, for anybody who hasn't seen imprecise probability, I want to just use a standard motivating example, which is the famous Ellsberg paradox. So we have an urn of 100 marbles, and 30 of the marbles are known to be red, and 70 of the marbles are blue or yellow in some unknown proportion. I don't know. Are they all blue? Are they all yellow? Is it some mix? I don't know. And now we're going to, of course, pick a marble from the urn. And here's an empirical fact. People typically, I don't have the exact percentages for you from an experiment. We could look that up. People typically prefer a bet that yields $1 if they draw a red marble and zero otherwise, over a bet that yields $1 if they draw a blue marble and zero otherwise. I probably should have asked you for your intuition about this example. Okay, would you prefer the bet that pays $1 for red and zero otherwise, or would you prefer the bet that yields $1 for blue and zero otherwise? But many people do. And this suggests, if I can infer something from your behavior, from your betting behavior, that you don't judge that drawing a blue marble is more likely than drawing a red marble. Because if you did judge that getting blue was more likely than red, why wouldn't you prefer the bet on blue? Okay. Yet, if we have a single probability representation of your uncertainty, well, then the obvious choice for a measure to represent your uncertainty would give the probability of a red marble as 0.3. And since you have no information to distinguish blue and yellow, it seems that you should assign those the same probability, namely 0.35. But if you do this, then you would have to judge that blue is strictly more likely than red. And by that, I just mean that blue is at least as likely as red and not vice versa. That's what, for now, this symbol means. Okay. So with a single probability representation, we're not apparently going to explain people's preferences. here's an alternative idea. If we do an imprecise probability representation, we could represent the agent with a set of probability measures. So I'll call these mu n, where n is some number between 0 and 70. And all the mu n assign probability 0.3 to drawing a red marble, and they assign n over 100 probability to drawing a blue marble, and then 70 minus n over 100 to drawing a yellow marble. Okay, so n is just the number of blue marbles. Okay, so this is supposed to represent the ambiguity, as the economists call it, the ambiguity of the situation, that you don't know the proportion of blue and yellow. And that ambiguity is reflected by having this plurality of many probability measures in your set. Now, in order to make a prediction about the preferences of an agent that is represented by such a set of measures, in other words, to give some empirical content to the claim that the agent is represented by this set of measures, I need some decision rule that tells you for two bets, which will they prefer. So let's, first, before I do that, let me just observe, and this is very important, that on this imprecise probability representation, you don't judge that red is at least as likely as blue, and you don't judge that blue is at least as likely as red. Because remember, to judge that would mean that all of your probability measures agree that red is at least as likely as blue. But they don't, because they, take n to be greater than 30, right? So not all of your probability measures say that red is at least as likely as blue, and not all of your probability measures say that blue is at least as likely as red. You could take n equals 0. So they're just incomparable. You don't make a judgment one way or another about which is more likely. Now let me get to the decision rule. So the standard kind of decision rule that people consider when you have a set of probability measures, for each measure in your set, you do an expected utility calculation for the bet that somebody is offering you. So for every measure, do an expected utility calculation. And then you just look at the lowest or worst case expected utility that you could get. You have all these expected utilities, one for each probability measure in your set. Look at the worst one, and you pick, if you're offered two bets, you pick the bet whose worst case expected utility is better. Okay. Now, if you do that, what you'll observe is that the agent will prefer the bet on red to the bet on blue. That's just because in the worst case, there could be 0 blue marbles. Okay, so the worst case expected utility of the bet on blue is worse than the worst case expected utility of the bet on red. So I hope this motivates a little bit what it would mean to attribute to an agent a set of probability measures in terms of how it would affect their decision making. Now, of course, you could also give an interpretation of a set of probability measures that is not pragmatic in this way, depending on how people are going to make decisions. You could just have a purely epistemic view of what it means to attribute a set of measures to an agent, and that's also a prominent view in philosophy. In cases where the evidence is not clear, maybe from a purely epistemic point of view, the agent should have a set of probability measures, or they should be represented by a set of probability measures rather than a precise single probability measure. Okay, back to the mathematical question, the representation question. Now, I'm going to go fairly quickly over these classic representation theorems in the interest of time, because I want to get to my new stuff about regularity. And you can look all this up in our papers and lots of other sources. But the famous sort of first result in this vein says, suppose you have a finite set of worlds and you have a binary relation on the power set. Then that binary relation is representable by a single probability measure. So I'm in the single probability measure case right now. If and only if the binary relation satisfies some axioms, okay? Some obvious axioms. A very important axiom when it comes to precise probability. This is a key commitment of precise probability. for any two propositions A and B, you either judge that A is at least as likely as B, or that B is at least as likely as A. And we're going to see that that goes out the window. Well, we just saw, actually, in the Ellsberg example, that goes out the window with imprecise probability. And many people think that's a benefit because many people thought that this is kind of a dubious commitment in the first place. Finally, there's an axiom called finite cancellation, which corresponds to finite additivity of the representing measure. And what this says is, if you look at every world in your set W, if every world belongs, you have two sequences of propositions, first of all. You have two sequences of propositions. If every world in your set belongs to exactly the same number of A propositions in your first sequence as it does to the B propositions. So every world, the first world might belong to exactly 7 of the A propositions and exactly 7 of the B propositions. The next world, the second world, might belong to 3 of the A propositions exactly and 3 of the B propositions exactly. So that's all that this is saying. Every world belongs to the same number of A propositions as B propositions. If that's the case, and you judge that for all I less than n, proposition AI is at least as likely as proposition BI, then to maintain the balance which comes from every world belonging to the same number of A's as B's, you have to think that Bn is at least as likely as An. If you thought that An is strictly more likely than Bn, well, that's actually impossible, you know, given the antecedents. Okay, so that takes a little bit of time to digest, but if you think about having a finitely additive probability function, so the soundness of this axiom is easy for finitely additive probability functions. Okay, so if every world belongs to the same number of A's as B's, and if your finitely additive probability function tells you that each of the AIs for I less than n is has at least as great measure as the BIs, then it's easy to see that your finitely additive probability function must say that Bn is at least as great measure as An. So that was kind of quick, but I just wanted to give you a taste of the key axioms for representation by a single probability function. Now, of course, what we're interested in is representation by a set of probability measures. So that's the next relevant representation theorem. So when is a binary relation representable by a set as the weak relation? Notice what's missing here, and I said this before, this comparability principle that any two propositions can be compared. A is at least as likely as B, or B is at least as likely as A. That's gone. Now you might think, and this is what I originally sort of thought before I saw this paper, maybe you just drop that comparability axiom. Maybe you just take this famous Kraft et al. Representation theorem, and then you cross this out, and maybe then those are the axioms that are necessary and sufficient for representation by a set of measures. It turns out, interestingly, that's not the case. You actually also have to strengthen the finite cancellation condition that I was explaining. So I'm not going to explain exactly the strengthening, this generalized finite cancellation condition. But it's interesting that you do have to take away the comparability axiom and then strengthen the finite cancellation condition. And we have a paper in which we actually prove that it really is a strengthening. So earlier representation theorems, they would give this stronger axiom, but wouldn't really prove that you actually need to have it. But we actually exhibited these comparative probability relations that satisfy finite cancellation, but not this generalized finite cancellation. Okay, so that's a little interesting detail. Now, I had mentioned the idea of representation as the weak relation. What's interesting when you go to sets of measures is there are actually two ways to define a strict relation. And then it's an interesting question of which one you should call more likely then. So the obvious idea is just take the asymmetric part of your weak relation. So this is the notation I'm going to use for A is at least as likely as B, but not vice versa. That's not the only way you can think about inducing a strict relation from your set. you could also think, what about unanimity among all measures that the measure of A is greater than the measure of B? So I will now use this symbol for that strict induced relation. Okay. So I find that intriguing that you can have two notions of strictly more likely than in the imprecise framework. And I will say that this relation is represented by P as the strict relation. Okay. I'm really not taking a philosophical stand there on, which one should you think in terms of for more likely than judgments, but I need some terminology to say when a binary relation is represented like this. Okay. So just as a simple example, suppose you have two measures, mu1 and mu2, and mu1 says that A and B have the same measure, and mu2 says the measure of A is greater than that of B. Okay. Well, then we would say that this first relation holds, but not the second, because it's not the case that every measure agrees that the measure of A is greater than the measure of B. Okay, so these are definitely different relations. And in the paper, we give sets of measures, P and P prime, whose weak relations are the same, but whose strict relations, in this sense, are different. And vice versa, we give sets whose strict relations are the same and whose weak relations are different. So neither is definable in terms of the other. That's important. Neither of these, the weak nor the strong, unanimity relation is definable in terms of the other. Now, of course, that means we should be looking at pairs. We should be looking at pairs of two relations. And the representation question that we want to ask is when, or what are the necessary and sufficient conditions such that the first relation is represented as the weak relation of the set of measures, and the second is represented as the strict relation. Okay. And I'll just give you the good news without going into the details, which is that you can get an elegant representation theorem for this setting where you have a pair of relations. And you just need to have a modified cancellation condition. But again, I don't want to really go into all the details here. Now, what do we do with all these representation theorems? I mean, that's interesting in and of itself. And I sort of consider this to be part of logic. But you might say, give me the formal language so we can start talking about complete logics. So that's what I'm going to do now. So here's the formal language. It's sort of just what you would expect. It's a propositional modal language. And I've got, primitive modalities, binary modalities for both the weak and the strict relation. And, what is a model? Well, I've got a set of worlds and I've got a propositional valuation. And now I'm evaluating these things, of course, also with respect to a set of probability measures. So that's what that P is. It's a set of probability measures. So I give the semantics that you would expect based on the notions of representation that I exhibited before. Okay, so this one just says that for all measures mu in my set, the measure of, this is just the set of worlds where phi is true. That's at least as great as the measure of the set of worlds where psi is true. Okay, and similarly for the strict relation. So it's just the obvious semantics. And then what we do in the paper is we basically translate that representation theorem into, we translate the conditions of that representation theorem into axioms in this language. So that gives us a logic, which we call IP, for imprecise probability. And what we do in the paper is we prove that that logic is sound and complete with respect to imprecise probability semantics. Okay. By that, I just mean that you have a set of worlds, you have a propositional valuation, and you have a set of probability measures, and you use this semantics. Okay. Later on, I will talk about models with even more structure than that. But for now, we have simple imprecise probability semantics. Okay. So by the way, I'm trying to focus on the big ideas rather than details. That's why I'm not showing you the whole axiomatization. But the axiomatization pretty much looks just like the representation theorem, but just translated into the formal language. Now what we want to do is we have our base logic for imprecise probabilistic reasoning. And now we want to add those bells and whistles that I mentioned before. So the first is a possibility modal diamond. And this possibility modal has an interesting semantics, actually. And one reason we want to add it, several reasons, but one is, in addition to making claims about factual states of affairs, like it is possible that it is raining, we also want to make claims about the possibility of likelihood relations. So we want to be able to say it is possible that hail is more likely than lightning tonight. Okay. How can we do that? Well, we do it by saying that diamond phi is true in this model relative to this set of measures at this world, just in case there is some measure in your set such that phi, when evaluated according to that measure as your only measure, so you sort of take the perspective of that probability measure. So this is, again, just the set of worlds where phi is true, at M relative to this set of measures. From the perspective of mu, phi has non-zero probability. So that's what the diamond says. The diamond says there is some measure in your set such that from the point of view of that measure, phi has non-zero probability. So that's how I can say it's possible that hail is more likely than lightning tonight. That means there's at least one measure in my set such that according to that measure, hail is more likely than lightning tonight. Now, we also axiomatize this, and we actually also prove this complexity result, that the complexity of the satisfiability problem remains NP complete for this language and semantics. Okay. So I'm not going to go through the complete logic. I will go through one logic for you, which is one of our dynamic logics, so don't worry. Yeah, dynamic logic of updating imprecise probability, this will use that diamond. So we're not going to leave that diamond behind. We're going to use that diamond in an essential way. So updating imprecise probability, here we are adopting a fairly standard idea for updating sets of probability measures. Well, very standard. So given a set P of probability measures, if you learn some proposition U with certainty, then you update your set P as follows. First of all, you only retain those measures, mu, which gave U non-zero probability. So you throw out of your set of measures all the ones that said that U had zero probability. You keep the rest, but you condition them on U. Okay, so you just do standard Bayesian conditioning on all of the measures that said, yeah, U has non-zero probability. So it's a shrinking of the set and then conditioning the remaining measures. Very standard idea. Now, one interesting thing, since we have a formal language with comparative probability operators, is that we can model updating on sentences containing not just factual formulas like it's raining, but also comparative formulas. So I can learn comparative formulas. So for instance, you might tell me it's raining and it's more likely that there will be hail than it is that there will be lightning. I can learn this. I can update on this. You can already see what this is going to do. The effect of my accepting this from you is that I'm going to discard from my set of measures all of those measures that don't say hail is more likely than lightning. Okay. And then I'm going to condition all the remaining ones on the fact that it's raining. Okay, so this is a way that I can actually come to have new comparative probabilistic beliefs. I can directly accept your comparative claims. Now, we want to go to dynamic logic. So we'll actually add to the formal language, in the spirit of public announcement logic and other dynamic epistemic logics. We're going to add this dynamic operator, this one right here. And this is going to say basically after learning phi, psi is the case. But what does learning mean? So first of all, as is usual in dynamic epistemic logic, there's a precondition for making the announcement. That is, in order for me to accept phi from you, it better be that there's at least one measure in my set according to which phi had non-zero probability. Right? Otherwise, my head explodes and I can't accept what you said. So there's got to be at least one measure that said that the content of your claim had non-zero probability. And if that's the case, then we simply update our set of measures by the formula phi. And by that, I just mean what I just said before, which is that we retain only those measures, new, that said that the truth set of phi had non-zero probability. And then we condition all of those remaining measures on the truth set of phi. And then after having done that, we check whether psi is true with respect to the new set of probability measures. So of course, this is a very standard approach in dynamic epistemic logic. Okay. Now, this is what I said before, that if we consider a formula like it's raining and hail is more likely than lightning, then the effect of that dynamic operator is just what I said. You discard all measures that don't satisfy h greater than L. Because if you don't satisfy h greater than L, then the probability, if a measure mu does not think that h is greater than L, then the probability, it says, for h greater than L is actually 0. That's an important fact. An important fact that I've smuggled in, which I haven't talked about yet, is that these comparative formulas are either true at all worlds or true at no worlds. We haven't yet represented some kind of higher order uncertainty, like where you don't know about your own uncertainty judgments. We're going to get to that. But so far, we've been working in this setting where the comparative formulas are either true at all worlds in the model or true at no worlds in the model. So that's why I say that if a particular measure mu doesn't think that h is at least as likely as L, then that formula will be false everywhere according to that measure. And that's why I throw out of my set of measures all of those that don't think that h is more likely than L. Okay. And then I condition the remaining measures on the fact that it's raining. Now, we're going to follow the standard technique in dynamic epistemic logic, the reduction axiom or recursion axiom approach, to get a complete logic that includes the dynamic operator. Okay. So what that means is we have a set of biconditionals, valid biconditionals, that actually allow us to rewrite any formula containing the dynamic operator to an equivalent formula containing no dynamic operators. And then, of course, we just invoke completeness of the logic without the dynamic operator. And that gives us completeness even in this expanded language. Okay, so these are some very familiar looking things in dynamic epistemic logic. And then the kind of interesting part from a probabilistic point of view is this axiom, or these two axioms, that get across the idea of conditioning. All right, so after you learn that phi is true, you judge that alpha is at least as likely as beta, if and only if. Well, first there's the precondition. You can't learn phi unless you at least considered phi possible. Okay, so setting that aside, what this is saying actually is that this box is actually quantifying over all the measures in your set. Right, the diamond said there is at least one measure, so the box says all the measures in my set think that phi and alpha is at least as likely as phi and beta. Okay, and of course that's just getting across the idea of Bayesian conditioning. You think that alpha is at least as likely as beta after you condition on phi, just in case in your original prior probability you thought that phi and alpha is at least as likely as phi and beta. So very simple, but then Bayesian conditioning is also very simple. Okay, and something similar holds for the strict relation, but you've got to be just a little bit more careful. So we get a sound and complete logic. Of course, as is typical in dynamic epistemic logic, there's an exponential blowup in the size of formulas when you apply these axioms to rewrite a formula containing dynamic operators to an equivalent formula without the dynamic operators, right? So there's a cost to getting rid of the dynamic operators. So this leads to an interesting open problem. Is there a satisfiability preserving translation with only polynomial blowup? So in the case of public announcement logic, that's a famous fact, well, in the dynamic epistemic logic community, that although the standard reduction axioms for public announcement logic, they result in an exponential blowup in the length of formulas when you get rid of the public announcement operators, you can be very clever, as Lutz was, and get not something that allows you to have a provable equivalence to a formula without dynamic operators, but at least a satisfiability preserving translation where you have only polynomial blowup. Now, of course, the nice thing about having these dynamic operators in a language is you can be exponentially more succinct in what you want to say relative to the static language without the dynamic operators. So it would also be nice to prove some succinctness results, like Lutz did for PAL, that shows, you really do get a gain in a formal sense in succinctness when you add the dynamic operators. Okay, so the next part of the dynamics is not just learning that something is true, but learning or becoming aware of a proposition or concept in the first place. So here's a little example to illustrate this. I mean, probably many of you are familiar with, awareness logic and that sort of thing. A patient learns from her doctor of the existence of a gland in the human body and a disease previously unknown to her. So she's never heard of any of this. Okay. The doctor informs her that if her gland is swollen, then it's more likely than not that she has the disease. Now, subsequently, the patient's gland is examined and she learns that it is in fact swollen. As a result, she concludes that it's more likely than not that she has the disease. Okay. So this is not a very implausible storyline, unfortunately, right? And we would like to be able to model each stage of this process, the becoming aware stage and the learning stage and drawing the ultimate conclusion. So how should we model this? And if you think about it for a minute, it's not easy to model this in the standard precise probability framework. Okay. You could say, when the agent was born, she had this extremely rich state space with every possible distinction that she was going to encounter in her life. And then she just conditions on, doctors telling her things, and everything works by Bayesian conditioning and so on. But actually, if you go to imprecise probability, you can have a much simpler representation where you just have the obvious kind of worlds, is my gland swollen? Is it not swollen? That's one distinction. Do I have the disease? Do I not have the disease? You can have a very small state space and still model this example nicely. Okay. So let me talk first about the language, and then I will talk about the semantics. So the language adds these new operators, IP, plus and minus, and the intended reading of IP plus is letting P be a true proposition that's newly introduced to the agent. Phi is then the case. And of course, you're going to expect that phi contains P. Otherwise, it would be a little bit uninteresting, right? And the minus is just saying that P is a false proposition that's newly introduced to the agent. Now, the agent won't know that this new proposition is true or false, but from the God's eye point of view of the modeler, we know whether the newly introduced proposition is true or false. And then we're going to have an abbreviation that IP phi just means it doesn't matter whether P is true or false. After we introduce P to the agent, phi is the case. Okay. Now, let me just give you a rough sketch of the semantics. You have to be a bit careful how you define this. And I've put a slide at the very end in case in Q&A if you want to know exactly how we define it. But roughly speaking, given a model and a set of probability measures, when we introduce a new proposition, what we do is we move to a new model and a new set of measures as follows. Well, we get the model by just splitting each of the old worlds in half. So we take every world W And we go to W comma 0 where P is false, and W comma 1 where P is true. Okay. This actually corresponds algebraically to a standard thing where you adjoin a new element to a Boolean algebra. But and it's nice to think about in terms of just splitting every world in half when you make this new distinction. Then we get a new set of probability measures, which we call split of P. This is the set of all measures on the resulting richer field of propositions. You now have more worlds, so you have more distinctions. The set of all measures on the new richer field of propositions, which agree with some old measure on all of the old propositions. Okay. And you can easily identify the old propositions. They're the ones that don't cross-cut the new distinction. Okay. So all of this can be made totally rigorous. I'm happy to do that. But hopefully that gives you a flavor. We split all the worlds, and then you become kind of maximally uncertain about the new distinction while retaining all of your old probabilistic relationships between old propositions. That's essentially what happens. Okay, then we do the standard thing where we evaluate one of these dynamic formulas by looking at the new model and the new set of measures. And the minus operation has you look at W comma 0, and the plus operation has you look at W comma 1. Okay, because after all, we need some world to evaluate things at. So we have to pick whether in this world, is it in fact the case that P is false or P is true? Okay. So then we can actually write down a formula in our language that represents that medical example that I talked about. If we take IP, or sorry, the proposition introduced by IP to be this new proposition that the agent has never thought about before, that the agent has the disease. And we take the proposition introduced by IQ to be another proposition the agent never thought about before, the gland is swollen. So now consider this formula. We're adding something that I didn't put in the story before, which is that when the doctor initially tells the patient of the existence of this disease, she feels fine. So she's like, more likely than not, I don't have the disease. Okay, so this is what happens. The doctor introduces this new proposition to her, the possible disease. She initially judges based on her feeling that it's more likely than not that she doesn't have the disease. Then the doctor introduces the concept of the swollen gland that's given by Q, and the doctor gives her this comparative information, which is that if your gland is swollen, then it's more likely than not that you have the disease. Okay. Then, after she learns that comparative statement, she then has the gland swollen and learns, unfortunately, that the gland is swollen. She has the gland examined, and then she learns that it's swollen. And that then results in the conclusion. She flips her judgment. She now thinks it's more likely that she has the disease than that she doesn't. Okay. And you can see that this is actually a valid formula according to the semantics that I've given. Okay. Now, what's interesting about this is that not only does it allow us to model these nice toy examples, is that it allows us actually to increase the expressivity of the language a lot. So we can actually express comparisons of linear combinations of probabilities with rational coefficients in this language. It's kind of interesting that by introducing propositions, you can now do these linear inequalities. And the basic idea of this is that you can introduce new propositions standing for independent coin flips coming up heads. And that allows you to now get all those rational inequalities. So for example, this sentence actually says that the probability of P is greater than 3/4. So what you do is you say, I've got these independent coin flips, Q and R. So Q is the proposition that the coin in my right hand comes up heads, and R is, well, Q, let's do left. Q is the proposition that the coin in my left hand comes up heads, and R is the proposition that the coin in my right hand comes up heads. And first I basically say, these are independent coin flips. Oh, and this of course just means, at least as likely and vice versa. Sorry, I didn't define that, but that's at least as likely in both directions. So I say I have these two independent coin flips, and then I say that P is more likely than it's not being the case that they both come up heads. Okay, so in this way, you can express things like P is greater than, the probability of P is greater than 3/4. And so there's a general fact here, which is that you can always write a formula that will express that the sum of the probabilities of the phi's, and here they're weighted by AI, is greater than or equal to the sum of the probabilities of the psi's weighted by the VI. So this is a big jump in expressivity, and that's a good news in one sense, but we also don't have a complete logic for this language. So I should have put that as an open problem. We would love to know, can we axiomatize this in a nice way? I mean, we can just say, we know from other results that it's decidable, but can we get a nice axiomatization of the logic of becoming aware? That's an open problem. Okay, the last part of my story, if I have a few more minutes left, is to talk about regular probability. So you may know that in philosophy, there's this long-standing, at least several decades, debate about what's called the principle of regularity. And this can be applied both to subjective probability and to objective chance. And very roughly, the principle says something like this: if a proposition A is possible, then it ought to have non-zero probability. Okay? And of course, we know from measure theory that, and I'll comment on this later, that we're all told that there are events, there are measure zero events that can nonetheless happen. But this is kind of pushing the other way and saying, no, if a proposition is really possible, then it ought to have non-zero probability. Now, why would you be motivated by this at all? Well, one oft-cited motivation is that, look, I want to be able to learn. And to learn A, at least by standard Bayesian conditioning, I have to have mu of A not zero. Otherwise, I can't condition. So that's a kind of, intuitive motivation for, if I want to be able to learn something, at least in the standard framework. People have proposed all kinds of other frameworks where I could learn even if something has probability zero. But vanilla Bayesian framework, in order to learn something, it has to have non-zero probability. So that's regularity, and I'll connect that to imprecise probability in just a second. But let me distinguish regularity, as Hofweber does, from a different principle. So Hofweber, this is a paper called Infinitesimal Chances, and he's discussing like objective chance rather than subjective probability. And he calls the following the minimal constraint that he thinks any theory of chance ought to obey, which is that if A has zero chance, then not A. Okay, you can just conclude not A. If A really has zero chance of happening, then not A. And he has an interesting discussion where he kind of considers this principle just beyond dispute when you're talking about objective chance, at least. So I want to consider both of these principles, regularity and the minimal constraint. I'm not going to get into the philosophical argument about these. I just want to understand how they relate to imprecise probability. Okay. So to do that, I need to go to richer models than I had before. Okay, so now a model for me is a quadruple. I have a non-empty set of worlds. Now I have a binary relation. Let's call that epistemic accessibility. I'm going to assume it's at least serial. So every world has a successor according to the relation. Then F is a function that assigns to each world a field of subsets of the set of accessible worlds. So as usual, R of W is just the set of all V, such that W are V. And finally, P is now not just a single set of measures, but is actually a function that assigns to each world a set of finitely additive probability measures on that distinguished field, F sub W. Okay. Now, these models allow you to represent higher order uncertainty. Like I could make judgments about, I think it's more likely that I have this probabilistic belief than I have that one. And you can also, these models naturally adapt to multi-agent models where perhaps this is most natural. So, I could make comparative probability judgments about your comparative probability judgments. I think it's more likely than not that you think, it's more likely to be sunny tomorrow than it is to rain, something like that. But for now, I'm just in the single agent case or the no agent case, if we're thinking more objectively. Now, a single probability measure is said to be regular if it assigns non-zero measure to every non-empty set in the field on which the measure is defined. Okay, so that's the standard definition of regularity. Non-zero probability assigned to every non-empty set in the field on which the measure is defined. Now, interestingly, with imprecise probability, since we have a set of measures, we actually have two notions of regularity: weakly regular and strongly. And they just differ by the quantifier. So we say that the whole model now, is weakly regular if for every world and every non-empty set in the field associated with that world, at least one of the measures says that the probability of X is non-zero. That's weak regularity. So you have to sort of consider it possible that X has non-zero probability. Whereas strong regularity is going to say that all of the measures in the set agree that that non-empty proposition X has non-zero measure. Okay. So now we have two notions of regularity. Just like we had two notions of strict preference, strict comparison, now we have two notions of regularity. So that's going to be the semantic correspondent, essentially, for regularity. And the semantic correspondent, essentially, there are some little details if you want to really do correspondence theory in the sense of modal logic. We need to put some constraints on these models. But essentially, the correspondent in quotes to the minimal constraint of Hofweber is what I'll call reflexivity. So say that a single measure is reflexive if it assigns non-zero probability to every true proposition in the field. And by true, I just mean every proposition that contains W. Okay. So then again, we get the same distinction between weakly reflexive, which says that for every world, for every proposition in the distinguished field for that world, if the proposition is true, then you have to assign it non-zero measure. And strongly regular says that all the measures give non-zero probability to all the true propositions. Okay, so that turns out to be the semantic correspondent. So one thing that's nice is Hofweber was just writing a philosophical article. It wasn't very formal, and he made this philosophical distinction between regularity and the minimal constraint. It's nice that that comes out so cleanly in the formal semantics. Now, as for logics, we need to say what the axioms are that correspond to regularity and the minimal constraint. So I'm going to add this dark diamond, which is now just the standard existential modality for the R relation. And the reason I'm coloring it in is to distinguish it from our earlier diamond, which did that non-zero probability test. So this just says there is some accessible world. Oh, sorry, that's a bad typo. There is some accessible world where phi is true. Okay, standard modal diamond. Now we can add two axioms that are sound for weakly regular and weakly reflexive models, respectively. Okay, the first, this is what regularity says, right? Regularity says phi is possible if and only if, and now to express this non-zero probability, we say it's not the case that bottom is at least as likely as phi. So it has a simple translation into the comparative language. Similarly, the minimal constraint also has a simple translation into the comparative language. The minimal constraint said that if phi has zero chance, then not phi. Well, we just say if bottom is at least as likely as phi, then not phi. Okay. Now, if we only have in the language the weak inequality, sorry, I have to keep correcting this typo, it just bothers me too much. If we only have in the language the weak inequality, then it turns out just by adding this axiom to the base logic of imprecise probability, we get a complete logic for not only weakly, but strongly regular models. And it just turns out that in this language, without the strict relation, even with strongly regular models, you don't pick up any additional validities. And if you want a logic for the minimal constraint, you just add this axiom instead. So it all works out very cleanly, axiomatically. And if we put the strict relation in the language, then we do actually pick up some additional validities over these regular models or the models that are reflexive. So you just have analogs that involve the strict relation. So those are the logical facts. And now let me end with a sort of an interesting question, philosophical question. Now that we've straightened out the logical facts. The logical fact is very clean logics when we want to go to regularity. Okay. So I want to end with this question. MC, the minimal constraint, that if phi has 0 chance, or in the comparative language, if bottom is at least as likely as phi. In other words, if phi is no more likely than a contradiction, then not phi, is that a plausible natural language inference? Now, of course, as I alluded to earlier, we've all been told when we got to the university that in infinite sample spaces, there are 0 probability events that can nonetheless happen. So the typical example of this is throwing darts at the 0-1 interval, with the Lebesgue measure. And you say, well, the probability of hitting any particular real is 0, but the dart's going to land somewhere. Okay, so we all, of course, get used to that in a measure theory setting. But I wonder, might MC be plausible just from the pre-theoretic natural language inference point of view? Might people agree, as this is an example on Twitter. I think this is the only time in my life I've ever invoked Twitter in an academic talk. Hopefully the last. We find a Twitter user saying, that's no more likely than walking off the edge of the planet, as a way of rejecting a claim in another tweet. Okay, and that's basically of this form, right? No more likely than some impossible event. So could it be that saying that's no more likely than something impossible is just a clever way of negating a proposition? In which case then, from the point of view of formal semantics of natural language, more likely than, maybe this is an inference that we would want to accept. That if phi is no more likely than a contradiction, then we can infer from that not phi. And this is really just an instance of a broader question that I find very interesting, which is, what's the relationship between natural language reasoning with more likely than and the mathematical theory of probability? Should we be giving the formal semantics for more likely than in terms of whatever we learn in our measure theory class? Is that somehow already implicit in ordinary thinking about uncertainty? This idea that there could be measure 0 events that can nonetheless happen, should we build that into our formal semantics for natural language? So I find that an interesting methodological question. And we discussed that in a semantics and linguistic theory paper in 2013 that you can find online. We don't discuss it for regularity, but we actually discuss it in the context of those axioms, finite cancellation axioms that we were giving you earlier. And we asked, are those somehow implicit in the practice of making at least as likely as judgments in natural language? So anyway, hopefully somebody will be interested in those methodological issues, not just in the clean logical results. So let me conclude by claiming, I hope I've given some indication that comparative probability still is a rich area for logical study. And I want to make a pedagogical proposal as well. Why don't we try this? When we teach Introduction to Logic, why don't we just introduce comparative probabilistic reasoning right after we introduce the Boolean connectives? I think that would be very interesting, to teach students some basic probabilistic reasoning, comparative probabilistic reasoning, right after we teach them some basic Boolean reasoning. Now, I must admit, I don't do this yet myself in my own Introduction to Logic courses, but I find it an intriguing idea. More on the research side, one thing I think is lacking is a more algebraic look at all of this. And then for the future, it would be nice to see new contacts between logic, probability, and hopefully also natural language semantics. So with that, let me just thanks again for the invitation and your attention.